In section 5.7, we'll be interpreting graphs of linear functions. Now, if we take a look at this graph here, okay, we kind of explored this graph in a previous video, but if we notice, where does the graph cross the vertical axes? Well, notice the graph crosses the vertical axis or the y-axis at 60. And where does the graph cross the horizontal? Well, in this graph, it doesn't. Will it ever cross the horizontal? No, not for this particular graph, it won't. And what is the rate of change of this graph? Well, my rate of change, again, remember, is equal to the change in the y divided by the change in the x, which is the change in the dependent variable, which is 20, and the change in the independent is 100. So this would break down to be 0.2. And if you notice, there is these values 60 and 0.2 do show up in my linear equation. Okay, the 60, we call that the constant. That's the end of my equation. That's like the y-intercept. And here's my rate of change right here. So in this particular example, to find the total cost of my rental, it would be, my cost would be $60 plus 20 cents for every kilometer that I drive. Okay, any graph of a line that is not vertical represents a function. We call the functions that we're dealing with linear functions. The point on the graph where the graph intersects the horizontal axes is called the horizontal intercept or the x-intercept. Either x equals some number, we'll call it 7, say, or the coordinate 7, 0. The point where the graph intersects the vertical axes is called the vertical or y-intercept, and it is represented by either giving a number, say y equals 4, or the coordinate 0 and 4. Okay, let's take a look at our first example here, and this is the volume of gas in a scooter. So it wants to write the coordinate of the points where the graph intersects the axes. So we want to write out the coordinates where the graph intersects the axes. So this coordinate right here would be 0 and 8. And the coordinate down here would be 200 and 0. And we want to therefore determine the vertical and horizontal asymptotes. Well, this is my vertical and horizontal intercepts. Well, there's my x-intercept, and this is my y-intercept. What are the domain and range? Well, the domain for this graph goes from 0 to 200, and the range is going from 0 to 8. Now, I should probably backtrack here a little bit and not use x and y, because in this particular linear relation, my x value was d and my y value was v for volume. Okay, I want you to pause the video and give this one a try. Okay, we want to look for the vertical and horizontal intercepts. Okay, well right here I have an intercept of 0 and 9, and here I have an intercept of 45 and 0. And my domain is going to be 0 less than or equal to t less than or equal to 45. And my range is going to be 0 less than or equal to h less than or equal to 9. So the intercepts really help me with my range and my domain. Okay, so now we want to sketch a linear function, and there's a couple of ways we can do this. Number one, we could make a table of values, and I would suggest if we make a table of values to use 3 points to sketch the graph. Okay, so let's use a table of values. So the first table point I'm going to pick is 0. If I plug a 0 in for x, negative 2 times 0 is 0 plus 7 is 7. If I plug a 1 in for x, negative 2 times 1 is negative 2 plus 7 is 5. If I plug a 2 in for x, negative 2 times 2 is negative 4 plus 7 is 3. So again, I'm going to plot the graph starting at 0 and 7, right there. And our next point was at 1 and 5. So when it's 1, it's 5, and when it's 2, it was 3. And again, there would be my linear graph. And again, some features are particular about how you draw your graph. You should draw it all the way through the graph. I just want to make sure you have the correct 3 points. Make sure you have arrowheads on the end. If you draw it through the graph, that is perfectly fine. So this is using a mini table method, and this is the very accurate way to draw this graph. However, there's another way we could do it. So I'm just going to erase this, and if you need to watch this part again, you can always rewind the video. And I'm going to just look at the graph and try to plot it based on knowing what the y-intercept is and the rate of change. So my rate of change here is really -2 over 1, and my y-intercept is the value 7. So what we could do is we could start at 7. There's my graph. And now my rate of change is -2 and 1, which means I go down 2 and over 1 for my next point. Down 2 over 1, down 2 and over 1. And again, I'm going to get the exact same graph that I got the last time. And this method is nice when my rate of change or my y-intercept is a whole number. When my y-intercept is a fraction, sometimes the mini table method is better than using this method here. Okay, we want to sketch the functions -2 over 5x plus 3 and 12x minus 7 in different colors on the same grid. They want us to label each graph. So I'm going to do the rate of change method. So for function f, okay, f of x is -2 over 5x plus 3. So my rate of change is equal to -2 over 5, and my y-intercept is equal to 3. So I'm going to start at 3, and my rate of change was -2 over 5, which means I go down 2 and over 5, down 2, over 5. Therefore, I'm going to get a line that looks something like this. And there would be my function f of x. And they wanted us to label that. So this would be the graph f of x is equal to -2 over 5x plus 3. On my next graph, okay, I'm going to do that one blue. I should call this one g of x instead because my other one is f of x. So g of x is going to be equal to 12x minus 7. So in this case, my rate of change is 12 over 1, and my y-intercept is equal to -7. So using the y-intercept starting point, so -2, 4, 6, there's 7. To get to my next point, I go up 12 and over 1. So I'm going to have a very steep graph going through these 2 points. And if you look at the 2 equations, so this is g of x, which is equal to 12x minus 7. Notice that this rate of change is positive. That graph is going uphill. The red graph's rate of change is negative. The graph is going downhill. Okay, now we are going to try to find the equation if we're given the graph. So we're going to work backwards. So again, I would start, again, remember we know our equation is going to be y equals whatever my rate of change is, x, plus my y-intercept. Okay, well my y-intercept in this case is this point right here, which is plus 5. And to figure out my rate of change, which I'm going to plug in here, I'm going to start at, say, this point, and I'm going over 2, and I'm going up 2. So 2 over 2 means my rate of change is 1. My equation, if I just write it, would be x plus 5. Okay, for my next equation over here, I'll do this one in red. Again, we're going to be plugging into this formula here again. And this time my y-intercept is 2, so I'm going to have a plus 2 here. And now my rate of change going from here to here, I'm going down 2 and over 1. So my rise is -2, my run is 1, and it's going downhill. So my rate of change is -2x. So my equation is going to be y equals -2x plus 2. All right, given the following graphs, write the equation of the graphs A, B, and C in function notation. Okay, so let's start with graph A. So function notation is going to be f of x is equal to rate of change x plus the y-intercept. So my y-intercept in the first graph is plus 9. And my rate of change, if I go from this point to this point, whoops, this point, I'm going over 1 and up 1, 2, 3. Now, if you're not sure whether this point here crosses at the corner, you could take the x-intercept, which is -3. So I'm going over 3. I'm going up 9. So my rate of change is going to be 9 over 3, which is 3. So my first equation for A is going to be f of x is equal to 3x plus 9. Okay, our second graph we'll call g of x, and that will be graph B. This will be g of x. Again, we're going to be plugging into the same equation. So my y-intercept for that one is plus 2. And my rate of change, that looks like it's crossing a corner there. I'm going over 1, 2, 3. I'm going up 2, so it's going to be 2 over 3x plus 2. And for my last graph, okay, C, I'm going to call this one h of x. And again, we're going to be plugging into the same formula. So my y-intercept in this particular case is plus 2. And this time my rate of change, I'm going down 1, 2, 3, and over 1. So it's going to be -3x plus 2. And this is the graph of h of x. Notice this graph is going downhill when I look at it from left to right. So my rate of change is going to be negative. Okay, given the following graphs, write the equation again. Well, again, this is our horizontal line. And remember, a horizontal line has the equation y equals, and it goes to the point 5, and y is always 5, no matter what x is. This one here is a vertical line, and the vertical line is x equals 3, because the x coordinates are always 3, no matter what the y coordinates are. I remember we talked about this earlier. This was y-bucks. Okay, which graph has a rate of change of half and a vertical intercept of 6? Again, a y-intercept of 6. They both do, but it's the rate of change is positive, so right away we know the graph's going uphill. But to just verify, my change in my independent is 4, and going up it's 2, so 2 over 4 reduces to 1/2, so this would be the equation that has, the graph that has a rate of change of 1/2 and a vertical intercept of 6. Okay, pause the video and see if you can figure out the next one. Okay, taking a look at this one, hopefully you had a chance to look at it. Again, the vertical intercept is 100. The rate of change is -5, which means the graph has to be going downhill. So we know this has to be it. But let's just verify our rate of change. So I'm going down 100 and over 20. 100 divided by 20 is 5, and so just going downhill, it's -5. So yes, this one is correct. Okay, let's take a look at the next example. It's the cost of publishing a yearbook. It says the budget for publishing costs is $4,200. What is the maximum number of books that can be printed? Okay, well, let's first of all see if we can come up with an equation for this function. So for cost, in terms of x, we'll put it in function notation, is going to be, well, I know what my intercept is. It is 500. And my rate of change, I'm going from here to here. My change is 50, and my rise is 1,000. So my rate of change is going to be 1,000 divided by 50, and that is going to be 20. So it's going to be, my cost is 20x plus 500. Now, why are the points not joined in this graph? Well, they're not joined because you can't buy. You must publish. You probably have to produce books 50 at a time. Okay, so when you're publishing, they won't let you publish one book. You have to publish them probably in sets of 50. What are the domain and range of the functions? Well, the domain, pretty straightforward, is going to be 0, 50, 100, 150, and 200, and the range is going to be 500, 1500, 2500, 3500, and 4500. Okay, so that would be the range. Now, the budget for publishing costs is 4,200. What is the maximum number of books that can be printed? So I know the total cost to have is 4,200. So my equation again was cost was 20x plus 500. So therefore, I'm putting 4,200 in for the cost. If I subtract 500 over, I'm going to get 3,700 is equal to 20x. And if I take 3,700 and divide both sides by 20, I'm going to get 185 is equal to x, which in this last example, there should be n, I guess. It should be c of n. Sorry, it should be c of n because it's n here. So in this equation, I should be using n as well. So the number of books that could be produced, 4,200 would be 185. Okay, but if you had to do them in terms of a booklets of 50, because it looks like in our chart you can only do yearbooks in groups of 50. 185 is not a multiple of 50, so the closest multiple of 50 less than 185 would be 150. All right, so that is the end of section 5.7. So there's your assignment. There's a handout that also goes with this assignment, which I'll give to you in class. So please try those questions. If you have any questions, check the answers on the website.